Is it in presentation mode? Yep.
Okay,
great. Okay, thanks for the introduction, and thanks for the invite to be here today and join for the whole week. It's one of the things I really like about OpenFOAM is the community. So I met Lou and Daniela at the OpenFOAM workshop in Germany in, I think, 2018, 2019, over a few beers in the afternoon. And then we met again at the hackathon run by Ed. And so it's great that we've kept in touch, and now we meet again here, and of course, hopefully in the future. And that's what I really like about this whole OpenFOAM community. So today I want to talk about numerical wave tanks. And so I don't need to give too much of a detail about them because stuff that Ed just talked about before, and Christian, the next presenter, will be talking a lot about them. What you'll see is that most of the methods use the volume of fluid methods. And perhaps there's some good reasons for that, but we'd like to see kind of what other solvers are there in OpenFOAM, how well do they perform or don't they perform, and perhaps why haven't we seen them used so much, and could they be used more in the future. And so this is work I've done in collaboration with Christian Vint, the next presenter, and Paul Schmidt, who's from Queen's University in Belfast. So I'll just talk about that today. And so what we'll focus on today is two things: is the solvers, the alternative solvers, and the wave makers. And then that's what this kind of, this is based on the paper that we presented, and that's what this kind of focused on. And then in the discussion at the end of this presentation, we'll bring up a couple other points that probably should be considered as well. So looking at the solvers, the most popular method is the volume of fluid method. And you can find those in the solvers interfoam and inter-isofoam. It has the iso vector. So when you're trying to develop a numerical wave tank. So there are the equations that they solve. I don't need to go into detail for those, but I just put them up because I'll show them later when I'm talking about the wave makers. What you'll see is you have the normal momentum and continuity equation. And then for the volume of fluid, you need this extra equation, which is for the volume fraction of water or air. And so on the right, you see a bit of a diagram of how that's captured in the volume of fluid, where we have 1 in the cells with water, 0 for the air, and then at the interface, we have some kind of fraction. So the advantage of this is that it's the most universally applicable method. So you can capture breaking waves, green water and structures. Also, you have the air phase there as well, which can be important. So if you're looking at maximum loads, you need the air, and the compressibility of air becomes important. So there's a lot of situations where you want to include the air and the water. However, there are some disadvantages. One is that you have this additional equation you're solving for, so that's some additional computation you're doing, of course. Another one is you have a very high mesh resolution around the free surface. So in this picture here, that's just a kind of a cartoon picture. In reality, the mesh at the free surface is much, much more fine than that. So you need a lot of mesh cells around the free surface to capture it well. And then the next point is perhaps the worst one, is that you get these unphysical high air velocities around the free surface. So due to the momentum transfer in these cells that contain part air, part water, you end up giving a lot of momentum to the air, which has a low density, so ends up getting a high velocity. And if you're using adaptive time steps controlled by the current number, then that means that in the area where you have the smallest mesh cells, you also get these very large velocities, which makes your simulation run much, much slower time steps than it probably needs to do. So that can be a bit of a problem. So although this is the most general and probably, you might say, the best method, there are some applications where you don't actually need the kind of fidelity and all the things this is giving to you for the extra computational cost. So there could be cases where you might want to use a less computationally heavy method, and do those exist in OpenFOAM? So what are the other surface capturing techniques available in OpenFOAM? Well, there's a surface tracking, and there's the depth average equations. So surface tracking can be found in a solver called potential free surface foam, which is basically an extension of just the pimple foam solver, normal pimple foam, which is a single phase. So we can see on the right there, a picture of it. We don't need the air phase. We don't need a high resolution around the free surface. And what happens is in the solver, there's an extra boundary patch that's being implemented on the surface, which can calculate the free surface there. So you're given out the free surface. You don't need to implement wave probes and things like that to calculate it. You're just given that. It calculates it out of the equations. So that's nice. You need less mesh resolution, and you're solving for a single phase. But you can also see that what you're given out is a single valued function for the free surface. So at any x position, you're only ever going to get one value where the free surface is. Whereas if we have a look at a breaking wave, in one x position, you're going to get multiple positions where the free surface exists. So you obviously can't capture breaking waves in this case. The other one is a depth average equation, which exists in the solver shallow water foam. And in that case, the momentum, the equations for the velocity now become just a 2D vector for the velocity in the horizontal directions. And it's depth averaged. And the free surface, which is given by this kind of h plus h naught, the height, that is solved directly. So it's actually a variable that's solved for. So you can get the free surface out that way. And as you can see, we only have one cell in the vertical direction. So you have much, much, much less cells. And this can run very, very fast, as we'll see. So if we compare these different solvers, the volume of fluid, you'll find hundreds, if not a few thousand publications using interfoam for numerical wave tanks. If you're looking at potential free surface foam, you'll find two papers. One of them is this one, and the other one is another one done by Paul Schmidt from Queens, and that's it. I was glad to see Håkan Nielsen win the OpenFOAM award yesterday, because apart from these, the only other document you'll find is one that his student did many years ago. So when we started looking at this, we could find no information on potential free surface foam. I don't know who made it, why they made it, where it's been used, except for this one student project done from the Chalmers PhD course. So, so that's interesting, why that's never been used. And the other one is shallow water foam, and you'll find less than a dozen papers using shallow water foam for numerical wave tanks. So why is that? Well, one reason might be numerical wave makers, because interfoam comes with several wave generation and absorption toolboxes readily available. So you have, back in the day when I first started using OpenFOAM, we had waves to foam toolbox, and that took a fair bit of effort to try to install. And I remember in the forums, like Ed would be asking all these questions that I had as well, like, how do you install this? It's so hard. But nowadays you can get like IH foam. It comes for free. It's built in the box. And so wave generation and absorption used to be a kind of a headache of how do you implement that. Now it just comes free with interfoam and with inter-isofoam. But if you're trying to use some of these other solvers, you're back to that same headache. You're going to have to implement your own wave maker. So perhaps that's why one of the barriers that stops people using these other methods. Of course, there are other things that, of course, interfoam is more general. In a lot of cases, you wouldn't use these other solvers, but these other solvers are never even tried for a lot of cases. So, so to try to address that, we had a look at the wave makers, and this this diagram is done by my colleague Christian Vint. So it's looking at the different wave generation and absorption techniques. So there's a relaxation zone, which can do both absorption and generation. That's in the waves to foam toolbox. The static boundary and dynamic boundary, which you get with IH foam, that can do generation and absorption. Then you have mass source and impulse source methods for generating waves. And to absorb waves, you'll need something like a numerical beach, or the one down the bottom, K, which I think is maybe even the best method, is you just use cell stretching and make the domain go out to infinity, so you never actually get the waves reflected back. And when you use cell stretching, to get a large distance, you don't have to use that many cells. So it's quite an effective method, I found, though perhaps a bit underrated. Okay, so what we looked at implementing was an impulse source wave maker. So it looks something like this. You have a source region, you can see there in red, where you're adding impulse to the equations. And then you need a numerical beach to absorb the waves on either side. And I color these red and green because here you can see this is all that's needed to be added to the equations to achieve this. So we have just, you only touch the momentum equation, you don't have to touch the other equations. And for the wave generation, you can see there's this term RW. All that is just a vector of 0 and 1. So it defines where the impulse source region is. So in this red area, that will all be 1. Everywhere else in the tank is 0. So that's the only place we're going to be applying impulse. And then we apply some kind of this acceleration, and that's going to be a signal that changes with time. So if you want to create a sinusoidal wave, obviously you'll apply a sinusoidal signal there. And then the question, of course, is how large, what's the amplitude that should be to create a certain amplitude wave. Then you'll see for the beach, similarly, we have this, it applies a damping with a strength S that's proportional to the velocity. So where there's velocity, it applies some damping. You can see that we apply it only in the vertical direction. So if there's a vertical velocity, and you'll see why we do that later, that's for if you want to do waves and currents. So we have these two zones where we have a beach, which we can adjust the strength of it, and there's impulse source region. So the question is, okay, if we want to, there's our wave probe, and we want to have this particular wave signal. What do we have to put into there? What does this required input look like? And to do that, we use a calibration method. So in the top left, you can see there's our target wave in blue, and we just apply some arbitrary random input, and we get this resulting output wave, which isn't even close. What we do then is do a spectral analysis where we do a Fourier transform of the input, the target, and the result. And if the result at a certain frequency is, say, 10 times less than what the target is at that frequency, then for the input, we just multiply that frequency by 10. Likewise, if the phase of the resulting wave is off by, say, 45 degrees with respect to the target, then we just change the phase at that frequency of the input by 45 degrees. And so you can see after the first input, we're not close. By the second, okay, we're getting the amplitude a bit better, but we're still looks a bit off. We have the fifth calibration, it's looking pretty close. And then by the final calibration, we're looking pretty good. And so here we can see, keep in mind, this is a log scale on the y-axis. By 7 iterations, we have the error between the target and the resulting pretty good. So you might say, okay, that's a bit of a headache having to do 7 simulations before you even run your first simulation. Well, one thing is that if this is a plane wave, which most of the cases they are, you just have to do a 2D slice. So you can do your calibration on just one cell thick. You can run them quite quickly. You do your calibration, you get your input, and then you extend it in the other horizontal direction to get your full 3D tank using the same thing. So that isn't, that takes some headache off. But for the other methods as well, you'll have to usually have to do a calibration as well. So if you're using IH foam or waves to foam and you have a certain target location, you can type into the boundary what you want. But if you've got some numerical dissipation, you might find that actually my target wave's a few centimeters less than I wanted, so I'm gonna have to pump up the input a little bit. Or if you have a varying bathymetry, you're going to get a wave transformation, you're going to have to do some kind of calibration, because the equations or the theory, the analytical solutions you apply at the wave maker input aren't going to take into account the wave transformations you get throughout the wave tank if it has varying bathymetry. So this method takes all that into account, as we'll see later. Okay, for the beach, we have this S function, which is the strength. Now over the beach, you obviously want to slowly taper it up so you don't get this kind of numerical reflection. There's just one example function you could choose. And then it's governed by one equation, which is this S max. You'll see on the table there, we have just for one wavelength, we tried various different values of S max. And you can see that over a broad range of values, you can quickly calibrate it and get it down below about 1% reflection, which is, or if you use 2, 3 wavelengths using cell stretching, you can get this down to pretty much 0 if you want. So, but for one wavelength of beach zone, Getting down to around 1% is great. And if you compare that to a physical wave tank, that's just unheard of. I mean, in a physical wave tank, if you're getting 10% reflections, you're a state-of-the-art world-class facility. So as all us kind of open foamers know, this is one big advantage of doing numerical wave tanks, is that we can really get rid of this reflection problem quite easily. Okay, so now we've talked about how we kind of calibrate this, the impulse and the beach. So let's have a look at a comparison where we apply this method to the different solvers. So to the interfoam, inter-isofoam, potential free surface foam, and shallow water foam. So here's the test case. It's one of these focus waves. We saw them a lot in the blind test series run by Ed. They're a nice test case because you can, in the CFD short simulation, you can test a whole range of frequencies, and you can get some also some non-linearities in there and things like that. So it's a good test case. We've got a flat bottom here, so makes life kind of simple. How did they perform? So here we can see the target, we can see the results. And in this case, actually potential free surface foam, we got the best results. So obviously, this is just one test case. You can tweak around with the amount of calibration you do and things like that. So the point is that all these solvers here could capture this type of wave quite well. So if we're dealing with a flat bottom, we're dealing multi-frequency, all the solvers can do pretty well. We chose a case that had shallow water, so that gave shallow water foam a chance. Maybe if we chose a deeper water case, shallow water foam may not have done as well. So there is more testing to do here, but just to show that for a case like this, all these solvers work quite well. Okay, now something a bit more challenging. This is a classic benchmarking case from Dingerman, where we have this kind of shoal, and it's a kind of an aggressive shoal. You can see the water depth goes from 0.4 all the way up to 0.1. And you can see that wave probe 1 is just on the flat area, wave probe 2 is at the top of the shoal, and wave probe 3 is in the leeward side. So this is a comparison of interfoam versus the experiments, and it did quite well at all the different locations. So interfoam with good calibration, mesh convergence, all that, it worked well. So interfoam could handle a case like this, no problems. When we look at the other solvers here, we can see that at the first wave probe, where we're still on flat bottom, they all are pretty much identical. Wave probe 2, which is the middle one, we get to the top of the shoal and you can see some differences. And then on the leeward shoal, you can see that the potential foam and shallow water foam didn't capture this, well, didn't capture the, with these kind of high frequency additions. So it depends on the accuracy you're after, I suppose. I mean, it captured the overall trend quite well, but if you're looking for this high resolution, then it didn't do so well. But if we look at this table down the bottom, we can see the amount of cells they required. So shallow water foam only needed 8,000 cells, whereas interfoam needed 100 times more cells than that. And potential free surface foam about 50 times more cells. And then we have this relative runtime. So that is for 1 second of simulation, how much real time. So you can see shallow water foam was a 13 times. So for this 70-second simulation, it took about 900 seconds to simulate. So 15 minutes, we could get a 70-second simulation, whereas in using interfoam, it's over 100 times more simulation time. So what you're getting kind of in 15 minutes for shallow water foam, you're waiting a couple of days for interfoam. So there you have to ask yourself, depends on your application, of course. I mean, if you really need this high resolution, which is maybe why you're using OpenFOAM, then sure. But in some cases, maybe using shallow water foam or potential free surface foam, the trade-off between the time required and the results may make you consider different options. So just a preliminary evaluation, we can see that you get significant efficiency gains by these alternative solvers compared to the volume of fluid. However, the range of applicability is not as wide. So the VoFs are great. I mean, you can, there you're kind of silver bullet that will hit anything. Whereas the other ones, there are some cases they could be applied, but not all cases for sure. But however, we didn't look at all kind of things. So like we need to look more at things like wave structure interaction. So if we're interested in, say, the forces or the pressure in a body, how well do these other ones do? For example, shallow water foams only going to give you an average value of the whole depth, which isn't going to give you information on the change with depth on some of these things. Floating bodies, moving bodies. Are you going to implement something like the overset mesh in these other ones? I'm not so sure. How do you deal with a floating body in these other potential foam and shallow water foam? Maybe you can't. So that's something else we need to further study. Waves and currents we'll look at in a second. Some can, others may have some bit more challenge doing those. And then perhaps domain decomposition strategies may be useful, where we use one of these other ones, as Ed showed before, where we had the quali or quail for foam. We use a potential foam in for the wave propagation and the Navier-Stokes in the middle. I also saw a nice paper recently by the guys at Cantabria where they do a domain decomposition of 2D to 3D. I thought that was really cool, and that's going to save a lot of simulation time as well. So how these things work with domain decomposition could be interesting to further evaluate as well. Regarding the impulse wave maker, so one thing we want to look at is implementing it through FV options. So at the moment, when we added, it's not big changes you had to make. We just had to add some extra fields to be available, and then just add those 1 or 2 terms to the, one term for the wave maker, one term for the beach, the equations, and then recompile. However, a lot of new users having to recompile new solvers, that's not always so easy. However, all you have to do is just add an FE options one file to your simulation, and you have this wave maker available for kind of any solver. That could be a strong advantage. So we want to look at implementing. We've already started doing that, and it looks promising. We've got 1 or 2 hurdles just to get over, but I think we can implement this through an FE options file, and you just include the file, and all of a sudden interfoam is now numerical wave tank, 1 file, and potential foam is now wave tank as well. We want to reduce this calibration overhead using machine learning. So at the moment, you have to kind of do 7 calibration iterations, but what we'd like to do is use machine learning, where if you know your wave spectrum, you know your kind of bottom topology, kind of create some kind of transfer function between what the input and the output is. So eventually, I guess what we could see happening, some kind of Python script or Octave script where you say this is the wave I want. You give an input time series for the desired wave, the distance between your wave maker and your wave probes, and the kind of bottom topology. And then it automatically creates the FV options file for you, and it makes the input time series required. So it would just be a Python script that you then include, and it can create this into a wave tank that can make any wave that you like. And the other thing we need to look at is multi-source regions. So we might need to use different length sources for different frequency bands, and also different source regions for the current generation. So just a quick look at that is, the kind of question is, what size should the source region be? So we had a look at this to do a parametric study. And if you look at the top at the interfoam source, along the, I don't know what axis you want to call that, but one of the horizontal axes, you see the source length. And you can see that when it goes above kind of half a wavelength, the error increases a lot. And we get a minimum around about 1/4 of a wavelength. So why is that? Well, if you think of this, this is the horizontal velocity of a wave. So there you have a wave series, and you can kind of see at for half the wave phase, you kind of have the velocity, horizontal velocity in one direction, and the other half, it's in the other direction. So if that is our impulse source region, and we're applying impulse there from left to right, then for half the wave, we're pushing impulse against the direction the wave actually wants to be. So that's a bad thing. Okay, so what if we reduce it by half? We have half a wavelength. Okay, that's better. But there's going to be some parts of the wave where we're still overlapping between velocity in one direction and velocity in the other direction. So if we reduce it to about 1/4, it does quite well. I mean, if you make it too small, then to create a certain wave of a certain amplitude, you're gonna have to apply a lot of impulse over a very small region and have a kind of big discontinuity, and that's not so good either. You're gonna get this kind of non-linear spillage out of it. So you want a decent size, but it can't be too big because then you're gonna overlap between the different velocity directions. So we found a quarter of a wavelength is kind of ideal. The other, the question is, okay, quarter of a wavelength, but if you have a wave spectrum, you have a whole bunch of wavelengths in there. So how do we deal with that? So what we're looking at now is implementing several kind of impulse regions. We think maybe we're looking at what the optimum is for a certain general kind of John swap, or even if you get these kind of Ochi-Hobble spectrums, which have like a 12 wave component and a C wave component. So you may have these dual banded spectrums. So you may want to have a different box for each one of those. And the other thing we're looking at as well is, at the moment, the impulse source is constant in the vertical direction, but as you know, kind of the waves decay exponentially with depth. So we're also looking at changing that impulse source region to kind of decay exponentially with depth as well, to depending on the wavelength. So we're looking at making some improvements that way. But we already found that it achieved quite well for most waves we were trying to get anyway, but we can always make things better. And then finally, waves and currents. So here, this kind of nice rainbow picture made by Christian as well. You can see that that's the beach strength. So you can see we hide the current source in between the beaches, and we have cyclic boundary conditions there. So we create the wave, and it's kind of traveling from left to right. It goes through the cyclic boundary, it comes through and gets absorbed by the beach. And as I mentioned, the beaches are only absorbing vertical velocities. So we keep the horizontal velocities because at the current source, we might say, okay, we want a 2 meter per second current. So we measure the current there, and if the current is 1.9 meters per second, we give it a bit of a push. So that way, if the wave was there as well, and we had this wave horizontal components, it would mess up our calibration of the current. So where the current source is, there's no waves. It's in between the two beaches. And then we push horizontal velocity out. It goes through the beaches. It doesn't see the beaches because the beaches only absorb vertically. And then on the other side of that, we have our wave source. And that's how we've been implementing waves and currents. So one problem is this may not work for shallow water foam because you can't absorb the vertical velocity because we don't have that. So how we do waves and currents with the shallow water foam, that needs to be considered as well. Okay, so that's a kind of quick overview of these kind of other solver options and wave makers for numerical wave tanks. And